Hi everybody, it's Mrs. Casil. Here we are. We're going to be going over your kinematics solutions. So I'll try to fit this all in one video, but it might be broken into two, so bear with me. So, number 9. Object B is faster because it has a steeper slope. This is incorrect because if you observe your graph, it is a velocity versus time graph. If you think about what the slope of a velocity versus time graph is, our rise over run is our change in our y-coordinate, which in this case would be a change in velocity, divided by the change in our x-coordinate. This is acceleration. So, the error in this student's statement is that the slope is what denotes acceleration. In that sense, they're correct. Object B has a greater acceleration, but the velocity of object A is at all points higher than object B. Think about, imagine numbers 0, 1, 2, 3, 4, 5. At every single point, that's a higher velocity than object B that maybe is starting at 1, going up to 6. Some people argued that later, object B would exceed the velocity of object A. That is true. So this main question was only about this part though. So for the most part, I only analyzed that. Alright, number 10. So Carmela and Desi. So this one, when we look at the key information that's here, we have Desi leaving first with an acceleration of 4 meters per second for 6 seconds. So that means on the graph, when time equals 0, that's what I'm assuming this leaving first means. Again, we have a velocity versus time graph, so I know that my slope is equal to my acceleration. So if he's got an acceleration of 4 meters per second squared, then for those first 6 seconds, he's going to have an acceleration of 4 meters every second, which means he's going to reach a top speed of 24 meters per second. He is obviously driving a car. So here's Desi. When we look at Carmela, on the other hand, she's starting 2 seconds after Desi. Her acceleration is 3 meters per second, and it's 10 seconds. So she's starting at 2, not at 0, because 2 seconds later she begins. And she's going for a total of 10 seconds. That means that she's accelerating for up to the 12-second mark, and that's when she is going to finally reach 30 meters per second squared. Excuse me, I'll say it wrong several times. This is 30 meters per second, and this is 24. So that maximum velocity that they each reach is like that. Question 11. Algebraic proofs are fun and challenging. What I would do is what I told you all in class. I would seriously just cover up the equation. I'm going to fold up a little piece of paper to cover it up right there so that I can't see what the equation is. The whole idea of this problem is I want to find an equation for stopping distance where it includes the initial speed of the car and the reaction time. That's what's making this a different problem. And then a constant acceleration once they slam on the brakes. So this is telling me that the reaction time, the car is going to be traveling, so it'll go some distance. And then there's the braking distance where the car is decelerating. And that's going to equal the total stopping distance. That's why they're writing it like this, right? So I've got my car traveling along here. And for a while, it's going at a constant velocity. And then up here, a fluffy puppy jumps out. That's a puppy, obviously. Doesn't it look like a fluffy puppy? Fluffy puppy. Okay, so fluffy puppy jumps out in front of the road. And then the driver slams on the brakes. It takes a second, or not literally a second, it takes some time for them to react, and then they slam on the brakes and they begin decelerating so that they hopefully come to a stop before they run into the fluffy puppy, right? So we have two parts to the problem here, so I'm going to analyze each part separately. The first part here is where I have this unlisted velocity, but it's a constant velocity. There's no acceleration. And during this time is when the driver is reacting. They're given some unknown amount of time, but it's their reaction time. So I want to find out how far did they drive while they were reacting. Well, this is easy. I could even use my middle school equation for distance over time. And if I solve this for the distance traveled while they're reacting, well, it's my initial velocity times my reaction time. And you'll notice that's what's right here, the first term in our equation that we're given. I'm going to focus the camera real quick. Sure, doesn't it seem like fuzzy over here? All right, whatever. The second part of our trip here is while the brakes have been slammed on. Here we're starting with this initial velocity, but it's no longer constant. Now we have some acceleration that's constant because we've slammed on the brakes, and we want to know how far we're going to go. The thing that's left out here is the braking time. Think about it. If you see a fluffy puppy jump out in front of your car, do you look at your watch to see how much time it takes for you to come to a stop? No, you stare at that fluffy puppy in front of you and you're watching the distance decrease and hoping that you come to a stop, meaning final velocity equals 0, before you run into that fluffy puppy. So I'm going to choose an equation where time is not one of my variables. I'm going to use my braking distance instead of my delta x for displacement like usual. So I'm trying to solve for what that braking distance is. So I'm going to do the algebra that's there. So VF squared minus VI squared is 2. Alright, so what I get is that my braking distance is equal to, before I write it, final velocity is 0, right? So I've got a minus VI squared over 2A, which, if you look back up at your equation now, is your second term. Number 12. Biggest thing to keep in mind in this problem is that we have two objects. We've got the truck that's approaching here with these poles that are 25 meters apart. Constant velocity here. Distance is 25 meters. That is one object. And then we've got James Bond standing on top of what some students told me looked like a giant pair of pants. And he's going to jump and hope to land in the bed of the truck when the truck arrives right here. The truck's motion is separate from James Bond's motion. So we have two different objects moving. James Bond is going to jump from this height, which means when he steps off the ledge, he's going 0 meters per second in the vertical direction. His final velocity, who cares what it is? Because we just want to know, does he get in the truck or not? If he breaks his legs, that's his own business. We want to know what his displacement is. Well, his initial position is 12 meters above the ground. He wants to end in the truck. So his displacement is at 10.5 meters. And he's falling with the acceleration of gravity, which if down is the negative direction here, because my displacement was downward and it was negative, This needs to be -2. Or let's make it easier for ourselves. Let's say down is the positive direction. So I'm going to choose an equation. He's trying to time his jump, right? So I want to find the time he falls, because that's what he's going to be able to judge, is how much time he'll be in the air. So I'm going to choose an equation that includes time. And joyfully, because my initial velocity is 0, this equation becomes a lot easier to work with. You can do the algebra yourself. I get an equation like this. So if I plug in my values for my time there, 2 times 10.5, that was the most common error that people made, was they put 12 in right here. Okay, and if I look at my calculator, check out my rad calculator, you guys. 2 times 10.5 divided by 9.81, and then I take the square root of that, 1.46. That's a time, so that's seconds. Now, a lot of you figured out that if I'm going 25 meters per second and the poles are 25 meters apart, that means that this takes 1 second for me to go that whole distance. So it's 1 pole per second, which means that if this is how much time it takes, he needs to jump at 1.46 poles. Or you could have estimated 1.5 poles, right? 1.5 poles is a pretty good jump. 1 pole, he would not make it. 2 poles, he would not make it either. Okay? Number 13. For this one, we're looking at graphs of velocity versus time again. And I want to find the acceleration. I already know that a velocity versus time, that slope is my acceleration. So if I want to know anything about the acceleration of these objects, I need to find the slopes of the line. So what I'm going to do is find the slopes. Oh, that's a 2. Pretend that's a 2. I do that by looking at the line. Oops, and I left off my negative sign. If you don't know how to find the slope of a line, that'd be a great thing to review. It doesn't matter which quadrant it's in, because see, look, it's the same slope in either location. So, A, B, and C all have the same slope. E and F have the same slope, but it's less than A, B, and C, and then D has the smallest slope. So none of these ors are correct. So your explanation needs to be about that the slope of a line tells us the acceleration on a velocity versus time graph, and that you have to include, it is important, that a positive number is always going to be greater than a negative number, unless we're thinking about just the magnitude. Okay. Last 2 questions. Oh, I could almost fit it in the video. Here we go. We're going to try. So, I determine the velocity during the first 10 meters of a 100-meter dash from a sprinter from start to rest. Okay. I want to find the acceleration. I know the displacement is 10 meters. My time is 2 seconds. My initial velocity is 0. My final velocity is left out. And I want to find my acceleration. So I'm going to choose an equation that does not include final velocity. So my acceleration is going to be equal. So I've got 2 times 10 divided by 2 seconds squared equals 5 meters per second squared. For part B, the sprinter's velocity after 2 seconds have elapsed. Oh, but I'm going to run out of time on my little video here, so I'm going to pause it.